So test review number 2 is just all of our rules for derivatives. So throughout this packet, if I were to go through real quick, you're going to see pretty much every type of derivative we've taken throughout the course of the year. Here's another set with all the inverse trig functions. Once we get through that, once you get to about number 26, all of these are different old types of AP questions that I've pulled off of old tests. A lot of them are pretty clever, definitely AP style as we work through here. For the most part, I am going to assume that we're pretty good with derivatives, so we're not going to do every single problem in this packet over a video. When I post this video onto Mastery Manager, I am also going to put the key for this with all the work on there, because I think probably this is one that you can kind of work through on your own at your own time, without me necessarily having to guide you all through all of these. And then as you're working, check your answers periodically, make sure you're doing these correctly. And if you had any questions, you could reach out. I'm really going to hit on the handful of questions that I think you might actually have questions on, where the other ones, even if you were to make a little mistake early, you would probably be able to figure it out, or the types of questions that are fairly common on the AP test that I want to make sure we're squared away on, okay? So this hopefully will be a little shorter than the last one and leave you some time to kind of work on your own. You'll have the answers to reference. So the three basic rules that we started the beginning of the year with were the chain rule, product rule, and then our quotient rule. All three of those are pretty critical. I can't imagine, no matter what version of the test they're creating for you guys, that those rules wouldn't get tested. So the chain rule is basically the outside-in idea. It's for composite functions. So if we were together this night, I would have you write this f of g of x. That's a composite. The way we take the derivative of a composite is always the outside term, so f prime. You would leave the inside of f alone, so g of x would stay the same. And then once we would have taken the derivative of f, we then multiply by the next outermost term, which is g. That would be g prime of x. And then the derivative of the innermost term here would have been 1. So that's our chain rule. The product rule is obviously when we have a product, where we would do the derivative of the first term, leave the second, and then we add the first term rewritten multiplied by the derivative of the second. The order here doesn't really matter. We could, if we want to, flip around those two combinations. Quotient rule is the one that the order is important. So this would obviously be if we have a quotient, f of x over g of x. Let me try to create a little space here, where we do the derivative, or sorry, the denominator unchanged, the derivative of the or the numerator, and then this is now a minus sign. That is why the order is important with this one. We then leave the numerator alone, the derivative of our denominator, and then all over our denominator squared. All right, that's a squared. So that's our three basic rules. You have to know those for sure. It's the basis of pretty much everything we did for most of the first semester. You'll see a whole bunch of problems here at the front. There's largely one of each of these. The big one that I want to do, the one that's the most common, is number 2. It's ones that I've given you periodically. These are probably the most common type that they like to test you on, if they're going to give you an actual function and not just a bunch of literal terms. Is number 2. This is the type that I've always recommended, and I would still recommend, even as we are better now at the end of the year, hopefully, at recognizing all of this, to take this squared term. That means the whole thing is squared. It's just easier to identify your insides and your outsides, so that when we take this derivative, this is our outermost term. So we're going to multiply by 2. It's just a power, so we do the power rule. And then subtract 1 from that power. So the 2 would have now become an exponent of 1. So you don't necessarily need to show that. Then you do times. Now we go inside. The outermost term of the inside parentheses is cosine. So we would take its derivative, which would be a negative sign, and we would leave its inside alone. So the 5x cubed stays the same. So we're now done with that term. The last part is the innermost term, which is that 5x cubed. Its derivative is 15x squared. Okay, then we simplify that, put all that together, and then that would be our answer. 3 is similar. We're not going to go all the way through 3. 3 is a product rule. So our product is here, but it is one that I would still strongly recommend before we do this. Hopefully we have this written down. If not, rewind me. I'm going to create a little bit of space here. That before we actually do the problem.
Hey, Dad?
Yes, bud. Okay, you just got paused as Isaiah interrupted me again. We're going to rewrite this whole thing as the quantity squared, and then it's a product rule. So this one's kind of lengthy. You can see the work online, but this is our first term, pretty simple for its derivative. But when we go to take the derivative of our second term, then we're doing the quotient rule, okay? So that's that. And the other one I want to make sure we do is number 5. It's a quotient rule. We haven't done a ton of quotient rules for a while, so that's one of the reasons. But then also the way that this one would get simplified, I want you to see. When these tests used to be multiple choice, this was fairly common. So we're going to do our denominator. The derivative of the top would just be sine of x minus the top, and then the derivative of our denominator would be 5. And then all of that is divided by your denominator squared. What we would then understand, hopefully, is that here's our first term. Here's the second term in our numerator. Each of these has a common 5 that we're going to pull out. So if I pull that 5 out, you will have x sine of x. And then the 5 has also been removed from this term. So I'll go ahead and get rid of the 5 and distribute that negative. Minus 1 plus cosine of x. And then all of that is divided by 25x squared. These are fairly common. Then what can happen is this 5 would get canceled, and it would reduce this 25 down to a 5x squared. All right, and then multiple choice wise, that's what you're going to be looking for. If this is all for your response, I don't think they're going to make a big deal out of you simplifying if they did give you something along those lines. All right, so moving along. Again, these we have not done in a little while, so I would like to do one of these. The main one being this guy. Just because the trickiest ones of these, once we do number 9, I think for sure you'll be able to do number 8 without a major problem, is when we have, this is clearly an x term, this is clearly a y term, but when we have that x and the y together, we're doing a product rule. But then the trickier part, and this is very, very common, is it's a product rule, but they have a little negative sign in front of it, and handling that negative is important, just to make sure we keep our signs straight. So when we do this, what this was us taking the derivative. There's no way we could solve this. We don't want to have to solve this for y and isolate the y all by itself and then do our derivative. We just took the derivative of this with respect to x right off the bat. So the first term would have been a 4x. But then when we come here, this is our product rule. And the first term, I always included the negative with our first term. So I'm going to say my first term is the negative 5x. And the y is going to be your second term. So when we do our product rule, the derivative of the first term would have been a negative 5. Leave your y. Product rule tells us we're supposed to add. The first term is a negative 5x, so we rewrite that. And then the derivative of y is y primed, or we always wrote it as dy dx. So that combo is important. That's the one you want to be careful of. And then the derivative of 7y, the 7 stays the same. The derivative of the y is dy dx, and then that would equal 0. Then we just went through isolating. So we would take these guys, move them to the other side. So we would get a positive 5y minus a 4x. And then these two, we're going to pull out the dy dx. So that would leave you with a negative 5x plus 7 times dy over dx. And then divide that over. So then our answer would be 5y minus 4x over a negative 5x plus 7. And then that's going to be your answer. Okay. 10, I want to do one of these too. It's your second. Oh, another thing about number 9. These are common free response questions, especially on the A-B test, the BC test you see in a little bit. A lot of times what they're going to ask you to do is figure out, where would this have a vertical tangent and we've done these. We did these with parametric and vectors. This would have a vertical tangent if your slope is undefined. So what that means is you would take your denominator, set that equal to 0. That's a fairly common follow-up to these with free response questions involving this type of a problem. If they ask you where do you have a horizontal tangent line, that just means the overall derivative gets set equal to 0. So as we multiply this over, this would have canceled, and then you just solve this for x or y, and then that a lot of times required us to plug back in to figure out our x or our y. Okay, so definitely be aware of that. If you were in the AB group, I would definitely tell you that's something that you want to be aware of. Now I'm just not so sure what we need to know quite as well as we used to. 10, second derivative with one of these. So obviously you need your first derivative to start. So derivative of x is a 1, 2y dy dx, and then the derivative of this y would be just a dy dx. That would equal a 0. If we then solved for dy dx, we would have taken the 1 and subtracted it over. And then we would have factored out this 2y and a 1 from those two terms and divided those over. So that's our first derivative. To take the second derivative now is just the derivative of that. So it's a quotient rule, 2y plus a 1, and then the derivative of your numerator, which is going to be a 0. Then we would subtract, you'd leave your numerator alone, and then the derivative of your denominator is 2 and then dy dx. And then all of that gets divided by your denominator squared. Then what you would notice is this is all going to cancel because of the 0. We see that we can turn this into just a positive 2, so that this would become a positive 2 dy dx over that 2y plus a 1 squared, quantity squared. And then what we needed to remember to do with this now, we want to replace this dy dx with what it had equaled here. So if you remember, we then took this, substituted this in, so that we would get 2 times a negative 1 over 2y plus 1, and then all of that divided by 2y plus 1 squared. Okay, now this one I give you a point, so you're going to go ahead and take that point, plug it in there, whatever that gives you your answer. You have hopefully the key in front of you, or it's on the computer, you can download, see what that is. I don't remember off the top of my head what that was. I'll be making the key for you in a little bit though. Okay, lines tangent, we've done a ton of these. Normal means we are perpendicular to our tangent line. So whatever slope we get, we would want the opposite reciprocal. Tangent then means they share a slope. So we always talked about how they share. Our line tangent and our curve share a slope, and then share a point. Again, if it was a regular AP test, you would get a handful of questions on lines tangent. That would be absolutely something that you would need to know. I would still strongly recommend knowing that. Pretty common. I can't imagine whatever version you're taking would involve a tangent line somewhere. Then we can use that tangent line to approximate things. A lot of times in BC, Euler's method. So Euler's method will be reviewed, obviously on down the road. So we'll probably dive into this a little bit more. That's where you really start doing some tangent line approximations, so on and so forth. So that's how we do tangents. And then the same here. Actually, maybe let's do this one, a little trickier. We want our point, and we know the x-coordinate is pi over 2. We just don't know our y, and then we would obviously need to figure out what our slope is. Once we can do that, then we can write the equation of our line. So if I know x is 2, the way I'm going to figure out my y is I'm going to go to the other side of this equation, and wherever I see an x, which happens to be my upper limit here, I need to plug in pi over 2. Let me just see I messed this up. So my x-coordinate here, come on, is, let me try this again, pi over 2, not 2. All right. And then we're integrating cosine of t dt. So again, this is later on down the road, but it's hard to find some questions that are specifically one topic only. So to find this value, what we need to do is evaluate that integral. So we would do the antiderivative of sine, which is cosine, from 0 to pi over 2. Plug in your upper limit minus the lower limit. And what our y value would equal is 1 minus 0. So we would then know our y coordinate is a 1. The derivative of this is your slope. So we would take the derivative of this equation. So this for certain would be on there as well. When we take the derivative of an integral, so if I can squeeze this in here with this fat pen, take the derivative of our integral, then these guys cancel. And the only thing that happens is whatever our variable limit gets plugged in for t. So in this case, we would just get the cosine of x. We would always multiply by that derivative of x, but in this case, that would just be a 1. That's our derivative. And then now we would want to evaluate our derivative at pi over 2. Cosine of pi over 2 is 0. So our slope ends up being a 0. Okay? So we can then write our equation, y minus 1 equals 0 times x minus pi over 2. All right. All right. The next set, spent a ton of time on these back in the day. For sure, these would always be something that would be a pretty critical part of the test. Derivative of a natural log and the derivative of an exponential function. These typically aren't terribly important. I can't imagine they're really going to focus on these guys, but just doing your due diligence, you would want to know everything just in case. So this 1 over u times du dx, e to the u repeats itself, and then the derivative of the exponent. These are essentially the same types of function. This is a unique exponential function when the base is e. So they both reproduce themselves. So a reproduces itself, just like e reproduces itself. Both of them, you have to take the derivative of the exponent. It's just with this one, you also have this middle element when you need to multiply by the natural log of your base. Okay. When we did common logs, we always rewrote those. So we always took this function here. We wrote the natural log of the composite, so that's where this comes from, divided by the natural log of your base. That's where this comes from. The base is a constant, so that because it is a constant, we pull it out. So that we're just ignoring this, and then all we're really left to do is to multiply that by the derivative of our natural log expression. Okay. So again, with these, I'm gonna again leave these to you a little bit. I'll leave you the key. You can kind of look through there. I think when you see the key, like, yeah, actually, you know what, 14. I do remember this every year. I tell myself I'm going to change that problem because it's silly. It's pretty tricky. It's kind of involved. I'll key it up if you're really concerned about it, but they wouldn't go crazy like that. 15, very, very common. You want to know that. 16 is just a basic rule. 17 is our common log. All of these, maybe 18 and 19, just so we make sure we have a good handle on this. The derivative, we're taking the derivative of this integral. So these operations would undo each other. So I need to take this variable limit, plug it in for t. So sine wouldn't change, the exponential function wouldn't change, but instead of e to the t, becomes now e to the natural log of x, and then you just have to always remember to carry out the chain rule. Didn't really matter with the one that we did earlier, but in this one we do, because the derivative of this guy, what we just plugged in, is 1 over x. And if we then simplify that, these would cancel. We get a sine of x, and then slot that x into your denominator. 19, very much AP style when they give you literal terms, where we don't really know what this function is, but we do know if I took the derivative of this integral, the function doesn't change. So like over here, sine didn't change. Whatever function we started with is the same function that we end with. So whatever this unknown function f would have been, it would have stayed the same in the next step. The only thing that would have changed is that this would have gotten substituted in for your t. So x cubed, that's a 3. and then multiply that by the derivative of what you just substituted in, which is 3x squared. Okay? All right, these guys, I, again, wouldn't anticipate you having to deal with these. These are when you have to take the natural log of both sides, when you have a variable raised to a variable. What that allows you to do, I'm not going to go through all this again. I don't think you're going to be able to have to know this. Get natural log of y on the other side, but now that we have the natural log of x to this power, I can take the power and pull it out in front. So if you ever have a variable raised to another variable expression, so here we have a variable as a base, we have a variable as an exponent, that's when you had to use that logarithmic differentiation. Okay. With these inverse trig derivatives, if you know inverse sine, then you know inverse cosine, because they're the same exact thing except one is negative. If we know inverse tangent, you know inverse cotangent, because inverse cotangent is negative. And if we know secant, you know inverse cosecant, because it's just a -1. All right. All right. So I'm going to, again, for the most part, leave you those. You have the formulas right here. Although, number 23. And again, maybe this is now not necessary because there is no multiple choice. But there was a multiple choice question on this on an old test that they were really kind of sneaky with. And very few of my kids got it. And you'll see why here in a minute. So we would be able to look up at the top, know what our derivative inverse sign is 1 over the square root of 1 minus u squared. U is always that inside term, so x over 2. So what most of my group did is they did that, simplified the inside, looked for that answer, and that answer was nowhere to be found. Because what they had them do, a lot of algebra here, they would have had the square root, and then if you recognize how this number 1 here could have been written as a 4 divided by a 4, so that we then have the same denominator. That allowed us to do 4 minus x squared over 4, and then that's all underneath the square root. Then we would hopefully understand that the square root of a fraction, which is what we have here, I can split into 2. So I would have square root of 4 minus x squared, all divided by a root 4. Oh, I forgot something too, by the way. Sorry. So easy it is to mess up. We would have had to have multiplied by the derivative of this. So we should have an extra 1/2 in front of all of these. So I'm just butchering this pretty good. All right. And then hopefully you're writing smaller than what I can with this pen. We have a 1 on top. And then this 2 is still in your denominator, multiplied by the square root of 4 minus x squared, all divided by, and then this root 4 became a 2. That cancels out that 2. And this was the multiple choice answer. That's what they had to somehow correlate to be from this and turn it into this, which is pretty hard. The nice thing, and hopefully they're going to give us some more direction this week, hopefully. If it's true response, they're not really concerned about you simplifying. So if you were to encounter this problem, this first step right here should be enough for the answer. If that changes, I'll let you know. All right, so a lot of mess there. All right, moving along. Again, for the most part, I think you can do 26 and 27. I have the answers for you. 28, 29. Solving equations on the AP test with your calculator. 28 and 29 both require you to do that. So when it says let f be a function given by, you're given f, you're given g, and then the functions are here and here. So we're given two functions, basic little setup. The question then asks, at what value of x do the graphs of f and g have parallel tangents? I may have given you this one, I don't know. This might be one you've seen before. Parallel tangents, basically think about what tangent lines, the slope of our tangent is our derivative. If they're going to be parallel, what that really tells us is their derivatives, f prime, has to be equal to g primed. That's when we're going to have parallel tangent lines, when their derivatives are equal. So that's our process. So take the derivative of f. Where are we at here? Eventually we'll get there. So the derivative of f would be 3 times e to the 2x times 2, which is 6e to the 2x. The derivative of g, very simple, 18x squared. They need to be set equal to each other. And then from here, it's a calculator question. So the way you're going to be solving these equations on your test is one of two ways. So if we're going to go with this one, what we need to do is to graph this underneath y sub 1, sub 1. Come on. Oh my God. All right, this underneath 2, and then you've got to look for the intersection. Okay. The other way, which is probably the safer way, because sometimes the intersection doesn't show up on a standard window, but the safer way is the 0, because as long as you can see your x-axis, then you should be able to calculate your 0. So the other way would be to subtract the 18x over so that it's equal to 0. Now we've only got to graph one equation. We would just graph this entire equation, and then you're going to do your 0 option on your calculator. Okay, so that's something that you want to be able to do. And when we do that, I don't remember off the top of my head. It was either C or D. Yeah, it was either C or D. I want to say it was C. But do that, do the intersection, give you a little practice on the calculator there. 29 is another one. Actually, I like this one. We won't go all the way through it, but you're going to write the equation of a line tangent. Again, very, very common. Typically what that would mean is we need a point, we need a slope. What you almost always need, or almost always are given, is the x or the y. Typically it's your x. In this case, what they give you is the derivative. So they're going to make you kind of rethink a little bit. They're giving you the slope. The slope is a 1. So our slope is our derivative. So if we took our derivative, x to the 4th plus 2x squared, set that equal to 1, since that's what our derivative value needs to equal. This looks like one that you would be able to solve by hand, but it doesn't factor anything. If it's on the calculator portion, then you would know that you almost have to certainly solve this with your calculator. But it's the same idea from up here. You either do the intersection at this step, or you move that 1 over, do the 0, and what that will give you is the x coordinate. So we'll then know this, and then once we know x, plug in x to figure out what your y value is, write your equation. Okay. That one I do remember is D, but you can kind of go through that and make sure we get that. All right. Again, for the most part with these are, again, every single one of these is from an old AP test. So it's good practice. Sit down, try it. God knows if you're like me, you got plenty of time on your hands sitting around the house to get some stuff done. All the answers are posted. The last one for sure that I want to show you that most everybody would ask about. Do I want to do one of these? Yeah, let's do one of these. Let's do 37. Yeah, this one was an old extra credit question on a test. That should look familiar to you. Yeah, let's do 36. So it's one of these where they don't give you a function. They just give it to you literally with some f's and g's and variables everywhere. That's AP style. Definitely want to be able to handle something like that, and that's what you're seeing in 36, 37, 38, 39, all stuff that is pretty common for them. So simple little setup in the sense that here's k. They want you to find k primed of 2. So we'd have to take our derivative, and then you'd have to recognize, how do I take the derivative of this? So this is our chain rule. If you come down here, this is our little shortcut where you're going to be taking the derivative of an integral. When you look at this literal function, they're testing you on both the quotient rule, and you're going to have to do the chain rule when we do the derivative of the numerator. We come down here, they're testing you on the chain rule. So they like testing you on all those rules without functions. They think that really tests you at a little bit higher level. So that's why they go with those. So that's what we're doing in 36 is the chain rule. You're going to do the derivative of the outside, f prime, leave the inside alone. Done with f. Then we go to g, take its derivative. Done with that. And then the derivative, I can squeeze this in, is 2x of the innermost term. You then plug in the 2 wherever you have an x. So we'd have f primed of g of 4 times g primed of 4. And then the 2 times the 2 will give us another 4. So now we got 4s everywhere. Then you use your table to get all those values. Okay, so f primed of g of 4 is a 1. All right, so here's g, here's 4, g of 4 is a 1. G primed of 4, so we go to our g column. We go to where 4 is at. Its value is a half times 4. And then our f primed of 1. So now here's f prime. Here is 1. So we would want 2/3 times a half times a 4th. Those will cancel. We get our 4/3. Okay. All right. I'll leave you 37. 38 you have seen before. You're doing the quotient rule, you're doing the chain rule. What you want to keep in mind, where we at 31 minutes. Yeah, why not, right? Where you're going to take your derivative. So let me do that up here so I have a little more room to write. So h primed, the quotient rule. So your denominator is unchanged. The derivative of the top, this is testing you on the chain rule now. You're going to do the derivative of the outermost term, which is g. So we're going to do g primed. You would have to leave its inside alone. And then times the derivative of the inside. When I gave this to you as an extra credit question on a test, it might not even been extra credit. A lot of us miss this 2 here, the derivative of the inside, and that was definitely one of the distractors. So be wary of that. Why is this stupid thing doing this all the time? Okay, I'm getting there. We said about 5 minutes just scrolling back, finding all these. So just be aware of that. Then we do minus the top. So g of 2x stays the same. And then the derivative of your denominator would be f primed of x. All divided by your denominator squared. Okay. Plug in 1. So f of 1. And then over here, don't ask me why now, it's looking weird either. Plug in a 1 right here, you would get g primed of ultimately 2. And times 2. A 1 plugged in right here would give you g of 2. And then over here, f primed of 1. All of that gets divided by f of 1 squared. So f of 1 here means you're going to go to the graph of f, go to where x is a 1, and its functional value is 4. The g primed of 2 means you're going to go to g, so here's g. You're going to go to the x value of 2, so right here. And since we want the derivative, that is our slope. So the derivative is the slope. That has a slope of a -1, and then we still do times 2. G of 2, go to g, go to where the x value is 2. We now want the functional value there, which is a -1. And then for this guy, f primed of 1 means we go to f. Here's f primed of 1. The slope there is 1. All over f of 1 squared, which we've already said is 4 squared. So that's 16. And then clean that up. So we get a negative 8 plus a 1 over 16. That's how we get our negative 7/16. Okay? Last problem we'll do together. This was an old free response question. So, pretty tricky stuff here. I can tell you, part A, when my kids came back this year, they didn't know how to do it. And when they post all the scores online for us to see around the country, the average score on this was ridiculously low because a lot of people didn't even know what question, particularly letter A, was even asking. So, all right. So you got to kind of remember the previous review that we had done. There's an important element to that review that applies here. So it says the functions f and g are differentiable for all real numbers, and then g is strictly increasing. So the first thing you want to recognize, and we talked about this in our last review, we really want to understand what they're giving us, what they're not giving us, and what does all of that mean. So the big thing here is they are telling you that our function is differentiable. What that then also guarantees is that our function must be continuous. All right. So at the last review, if you went through that, if you remember that, if you watched it recently, we've talked about when you start seeing the idea of continuous and differentiable, and then they start talking about things that must be true or that are false or whatever, what very, very, very often that means is they are going to at some point test you on the idea, if you kind of remember that before I write it. So continuous, differentiable things must or must not be true. What they're almost always going to be getting at is the mean value theorem. Okay, and that's what this question is. It's just not obvious, and they don't use those words anywhere. So it says the table above, I guess now it's below, gives the values of the functions and their first derivatives at selected values of x. So similar to stuff we've seen plenty of times. They then give you the function h. So notice h is not in your table. It's a different function. But what they tell you h is the composite of f of g of x minus 6. And then letter A is saying explain why there must be a value where between 1 and 3 where our derivative is equal to 5. So if you remember the mean value theorem up here, the mean value theorem says the instantaneous rate of change, that's our derivative. So that's this guy. This is our instantaneous rate of change. Must equal the average rate of change. And if you remember, the average rate of change is over an interval. So what they had to do here is understand that this was being tested, or you were being tested on the mean value theorem. And what we would need to know is then if I could show that h of 3 minus h of 1 equaled, or excuse me, over 3 minus 1, if this equaled a negative 5, then the mean value theorem guarantees, since we are continuous and differentiable, that somewhere in the interval of 1 to 3, our average rate of change, this here, must equal our instantaneous rate of change. So if we can prove that our average rate of change was a negative 5 by using our table, that's what would guarantee our instantaneous rate of change was somewhere equal to a negative 5. Hopefully that makes sense. Now we still have to kind of go through this problem and prove this. But if we don't get our problem to be a negative 5, then there's something wrong because they're telling you to explain why this must be true. So even understanding that, this is not easy because think about what h of 3 is going to be. That means you have to go to this function and plug in 3. So that would give you f of g of 3 minus 6. So whatever that evaluates to be is h of 3. Let me create a little space here. And then I would need to do h of 1. So I'm going to go to that function up above. I'm going to plug in a 1, f of g of 1 minus 6. And then all of that gets divided by 3 minus 1, which is a 2. So still some work to do. Go to your table, you got to find g of 3. So now I'm going to do f of, and then we need g of 3. So g of 3 is this 4 here, and then minus 6. Then I would need g of 1, so I'm going to do f of g of 1. So here is g of 1, so that's a 2, minus a 6. And we still got our little 2 in our denominator hanging out. I'm going to have to go down here. F of 4, so f of 4 is a negative 1. So we would do negative 1 minus 6 minus f of 2, which is 9, minus 6 over 2. And that would be a negative 7 minus 3 over 2. Not coincidentally, that gives us a negative 5. So since we have proved that our average rate of change, so here's our average rate of change, we just show that the average rate of change equaled a negative 5. What that then does, it guarantees must be a value where the instantaneous rate of change would equal a negative 5. Okay, you were supposed to explain it basically when we sat through here and they explained how the explanation had to go. Basically, within the explanation, as long as the expression mean value theorem made an appearance, that you demonstrated you understood you were dealing with the mean value theorem, then they gave you that explanation point. Okay. Tricky stuff there. Chances are, again, it's a little shorter test, lot shorter test, but I would have told you before, there are going to be questions that you just don't know how to do. They're going to find really creative ways to test you on things, and it's just, again, thinking out of the box, trying to figure out what they're getting at, and there's going to be a handful where you just say, I don't know. Move on, go to the next problem, okay? All right, then, last but not least, this one was much more doable for this question. This one, most people should get. Simple little setup. Here's W. You got to take the derivative and plug in a 3. So W primed of x. We're taking the derivative of an integral. So when we do that, the derivative and the integral cancel. We would do f of g of x multiplied by, because again, we're just taking the variable part. That's got to go in for our t. And then multiply that by the derivative of what you just plugged in, which would be g primed of x, and then the derivative of the innermost term x is just a 1. Plug in a 2. Use your table to get all these values. So w primed of 2 would then be f of g of 2 is 3. Uh-oh, what happened there? I don't know what's going on. Let me do this over here. So this would be f of g of 2. Just what, 3? G primed of 2 is 1. So final answer, f of 3. Where's f of 3? So g of 2 is 3. Okay, you probably caught my mistake. Sorry. So we need to get rid of all of this guy. You probably already know this. I don't know why I picked a 2 out of nowhere. We're doing w primed of 3, so we need a 3 here. So f of g of 3, try this again, times g primed of 3 would equal f of, and then g of 3, g of 3 is 4. G primed of 3 is 2. It's over here. F of 4, what is f of 4? I covered it up. Space there is a negative 1 times 2. Yeah, and then that was the answer. All right, so we should get negative 2. All right, 2 down. This is a pretty critical one. You're going to need to know your derivative rules really well. Again, any questions, reach out, let me know, and I'll do my best to help.